Geology is an earth science comprising the study of solid earth, the rocks of which it is composed, and the processes by which they change. Geology can also refer generally to the study of the solid features of any celestial body. Geology gives insight into the history of the Earth by providing the primary evidence for plate tectonics, the evolutionary history of life, and past climates. Geology is important for mineral and hydrocarbon exploration and exploitation, evaluating water resources, understanding of natural hazards, the remediation of environmental problems, and for providing insights into past climate change. Geology also plays a role in geotechnical engineering and is a major academic discipline. Geologic materials. The majority of geological data comes from research on solid earth materials. These typically fall into one of two categories: rock and unconsolidated material. Rock. There are three major types of rock: igneous, sedimentary, and metamorphic. The rock cycle is an important concept in geology which illustrates the relationships between these three types of rock and magma. When a rock crystallizes from melt, it is an igneous rock. This rock can be weathered and eroded, and then redeposited and lithified into a sedimentary rock, or be turned into a metamorphic rock due to heat and pressure that change the mineral content of the rock, which gives it a characteristic fabric. The sedimentary rock can then be subsequently turned into a metamorphic rock due to heat and pressure and is then weathered, eroded, deposited, and lithified, ultimately becoming a sedimentary rock. Sedimentary rock may also be re-eroded and redeposited, and metamorphic rock may also undergo additional metamorphism. All three types of rocks may be remelted. When this happens, a new magma is formed, from which an igneous rock may once again crystallize. The majority of research in geology is associated with the study of rock, as rock provides the primary record of the majority of the geologic history of the Earth. Unconsolidated material. Geologists also study unlithified material, which typically comes from more recent deposits. These materials are superficial deposits which lie above the bedrock. Because of this, the study of such material is often known as Quaternary Geology, after the recent Quaternary period. This includes the study of sediment and soils, including studies in geomorphology, sedimentology, and paleoclimatology. Whole Earth structure. Plate tectonics. In the 1960s, a series of discoveries, the most important of which was seafloor spreading, showed that the Earth's lithosphere, which includes the crust and rigid uppermost portion of the upper mantle, is separated into a number of tectonic plates that move across the plastically deforming, solid, upper mantle, which is called the asthenosphere. There is an intimate coupling between the movement of the plates on the surface and the convection of the mantle. Oceanic plate motions and mantle convection currents always move in the same direction, because the oceanic lithosphere is the rigid upper thermal boundary layer of the convecting mantle. This coupling between rigid plates moving on the surface of the Earth and the convecting mantle is called plate tectonics. The development of plate tectonics provided a physical basis for many observations of the solid Earth. Long linear regions of geologic features could be explained as plate boundaries. Mid-ocean ridges, high regions on the seafloor where hydrothermal vents and volcanoes exist, were explained as divergent boundaries, where two plates move apart. Arcs of volcanoes and earthquakes were explained as convergent boundaries, where one plate subducts under another. Transform boundaries, such as the San Andreas fault system, resulted in widespread powerful earthquakes. Plate tectonics also provided a mechanism for Alfred Wegener's theory of continental drift, in which the continents move across the surface of the Earth over geologic time. They also provided a driving force for crustal deformation, and a new setting for the observations of structural geology. The power of the theory of plate tectonics lies in its ability to combine all of these observations into a single theory of how the lithosphere moves over the convecting mantle. Earth structure advances in seismology, computer modeling, and mineralogy and crystallography at high temperatures and pressures give insights into the internal composition and structure of the Earth. Seismologists can use the arrival times of seismic waves in reverse to image the interior of the Earth. Early advances in this field showed the existence of a liquid outer core and a dense solid inner core. These advances led to the development of a layered model of the Earth, with a crust and lithosphere on top, the mantle below, and the outer core and inner core below that. More recently, seismologists have been able to create detailed images of wave speeds inside the Earth in the same way a doctor images a body in a CT scan. These images have led to a much more detailed view of the interior of the Earth, and have replaced the simplified layered model with a much more dynamic model. Mineralogists have been able to use the pressure and temperature data from the seismic and modeling studies alongside knowledge of the elemental composition of the Earth to reproduce these conditions in experimental settings and measure changes in crystal structure. These studies explain the chemical changes associated with the major seismic discontinuities in the mantle and show the crystallographic structures expected in the inner core of the Earth. Geologic time. The geologic time scale encompasses the history of the Earth. It is bracketed at the old end by the dates of the earliest solar system material at 4.567 Ga, and the age of the Earth at 4.54 Ga at the beginning of the informally recognized Hadean. At the young end of the scale, it is bracketed by the present day in the Holocene Epoch. Important milestones: 4.567 Ga. Solar system formation. 4.54 Ga. Accretion of Earth. c. 4 Ga. End of late heavy bombardment. First life. c. 3.5 Ga. Start of photosynthesis. c. 2.3 Ga. Oxygenated atmosphere. First snowball Earth. 730 to 635 Ma. Second snowball Earth. 542 plus or minus 0.3 Ma. Cambrian explosion, vast multiplication of hard-bodied life, first abundant fossils, start of the Paleozoic, c. 380 Ma. First vertebrate land animals, 250 Ma. Permian Triassic extinction. 90% of all land animals die, end of Paleozoic and beginning of Mesozoic, 66 Ma. Cretaceous Paleogene extinction, dinosaurs die, end of Mesozoic and beginning of Cenozoic, c. 7 Ma. First hominins appear, 3.9 Ma. First Australopithecus, direct ancestor to modern Homo sapiens, appear, 200 Ca. First modern Homo sapiens appear in East Africa. Brief time scale. The following four timelines show the geologic time scale. The first shows the entire time from the formation of the Earth to the present, but this compresses the most recent eon. Therefore, the second scale shows the most recent eon with an expanded scale. The second scale compresses the most recent era, so the most recent era is expanded in the third scale. Since the Quaternary is a very short period with short epochs, it is further expanded in the fourth scale. The second, third, and fourth timelines are therefore each subsections of their preceding timeline as indicated by asterisks. The Holocene is too small to be shown clearly on the third timeline on the right, another reason for expanding the fourth scale. The Pleistocene Epoch. Q stands for the Quaternary period. Millions of years dating methods. Geologists use a variety of methods to give both relative and absolute dates to geological events. They then use these dates to find the rates at which processes occur. Relative dating methods for relative dating were developed when geology first emerged as a formal science. Geologists still use the following principles today as a means to provide information about geologic history and the timing of geologic events. The principle of uniformitarianism states that the geologic processes observed in operation that modify the Earth's crust at present have worked in much the same way over geologic time. A fundamental principle of geology advanced by the 18th-century Scottish physician and geologist James Hutton is that the present is the key to the past. In Hutton's words, the past history of our globe must be explained by what can be seen to be happening now. The principle of intrusive relationships concerns cross-cutting intrusions. In geology, when an igneous intrusion cuts across a formation of sedimentary rock, it can be determined that the igneous intrusion is younger than the sedimentary rock. There are a number of different types of intrusions, including stocks, laccoliths, batholiths, sills and dikes. The principle of cross-cutting relationships pertains to the formation of faults and the age of the sequences through which they cut. Faults are younger than the rocks they cut. Accordingly, if a fault is found that penetrates some formations but not those on top of it, then the formations that were cut are older than the fault, and the ones that are not cut must be younger than the fault. Finding the key bed in these situations may help determine whether the fault is a normal fault or a thrust fault. The principle of inclusions and components states that, with sedimentary rocks, if inclusions are found in a formation, then the inclusions must be older than the formation that contains them. For example, in sedimentary rocks, it is common for gravel from an older formation to be ripped up and included in a new layer. A similar situation with igneous rocks occurs when xenoliths are found. These foreign bodies are picked up as magma or lava flows, and are incorporated later to cool in the matrix. As a result, xenoliths are older than the rock which contains them. The principle of original horizontality states that the deposition of sediments occurs as essentially horizontal beds. Observation of modern marine and non-marine sediments in a wide variety of environments supports this generalization. The principle of superposition states that a sedimentary rock layer in a tectonically undisturbed sequence is younger than the one beneath it and older than the one above it. Logically, a younger layer cannot slip beneath a layer previously deposited. This principle allows sedimentary layers to be viewed as a form of vertical timeline, a partial or complete record of the time elapsed from deposition of the lowest layer to deposition of the highest bed. The principle of faunal succession is based on the appearance of fossils in sedimentary rocks. As organisms exist at the same time period throughout the world, their presence or absence may be used to provide a relative age of the formations in which they are found, based on principles laid out by William Smith almost 100 years before the publication of Charles Darwin's theory of evolution. The principles of succession were developed independently of evolutionary thought. The principle becomes quite complex, however, given the uncertainties of fossilization, the localization of fossil types due to lateral changes in habitat, and that not all fossils may be found globally at the same time. Absolute dating. Geologists also use methods to determine the absolute age of rock samples and geological events. These dates are useful on their own and may also be used in conjunction with relative dating methods or to calibrate relative methods. At the beginning of the 20th century, important advancement in geological science was facilitated by the ability to obtain accurate absolute dates to geologic events using radioactive isotopes and other methods. This changed the understanding of geologic time. Previously, geologists could only use fossils and stratigraphic correlation to date sections of rock relative to one another. With isotopic dates, it became possible to assign absolute ages to rock units, and these absolute dates could be applied to fossil sequences in which there was datable material, converting the old relative ages into new absolute ages. For many geologic applications, isotope ratios of radioactive elements are measured in minerals that give the amount of time that has passed since a rock passed through its particular closure temperature, the point at which different radiometric isotopes stop diffusing into and out of the crystal lattice. These are used in geochronologic and thermochronologic studies. Common methods include uranium lead dating, potassium-argon dating, argon-argon dating, and uranium-thorium dating. These methods are used for a variety of applications. Dating of lava and volcanic ash layers found within a stratigraphic sequence can provide absolute age data for sedimentary rock units which do not contain radioactive isotopes and calibrate relative dating techniques. These methods can also be used to determine ages of pluton emplacement. Thermochemical techniques can be used to determine temperature profiles within the crust, the uplift of mountain ranges, and paleotopography. Fractionation of the lanthanide series elements is used to compute ages since rocks were removed from the mantle. Other methods are used for more recent events. Optically stimulated luminescence and cosmogenic radionuclide dating are used to date surfaces or erosion rates. Dendrochronology can also be used for the dating of landscapes. Radiocarbon dating is used for geologically young materials containing organic carbon.